Let's imagine together we've gone on an 8-month journey and arrived to the planet Mars. Yeah, Mars. Somehow we will have to figure out how to build protective and durable structure to shield us against solar radiation, galactic cosmic rays, and extreme temperature swings. On a Mars mission, there is only so much that we can bring with us from Earth, and it's prohibitively expensive to launch tons and tons of construction materials into space. So, to realize a pioneering habitat to progressively grow, adapt, and expand into a permanent outpost, we have to think differently about how we build. These habitats and the robots that build them will enable humanity to thrive off-world. I am a space architect. I design and conceive habitats supporting human exploration in deep space like on the surface on Mars. Not only do I design spaces for optimal crew health and performance, but I also investigate what these habitats are and how they are going to be built. Now, Mars is so far from us that communication delays can take up to 22 minutes one way to or from Earth. And what it means is that we can't rely on real-time telerobotics controlled by people on Earth to supervise what happens in construction on Mars, or for that matter, to supervise anything that happens when we are exploring the planets. But we leverage autonomous robotics will send 3D printers and other construction robots build protective habitats and shelters before the crew even arrives. So, how exactly would 3D printers build a habitat on Mars? Well, first we have to figure out what these structures are made out of. Just like early civilization will use in situ regolith, commonly known as dirt, and other resources that are local and indigenous to the planet, including water, and possibly combine them with additives and binders that we bring from Earth to engineer high-performance construction materials. Our goal when we are designing these habitats is to introduce an airtight structure that can withstand internal pressurization, which is what will allow people to live in a breathable and temperate environment on the inside. The robots that we deploy on Mars will need to perceive and interpret the complexity of a construction site in order to sequence and choreograph different types of tasks. These tasks will include prospecting Mars and surveying for a site to build, collecting raw materials, processing those materials, and maneuvering them around. Some of these spots might resemble the character Wall-E, except not so cute. Once the site has been excavated and foundations are printed, the structures are manufactured layer by layer by layer. And as construction progresses, pre-built and pre-integrated hardware like airlocks or life support equipment brought from Earth are inserted into the print until finally they are sealed at various connection points. To do more than just survive in space, we need to create environments that positively contribute to well-being for months and years into the future. And as more civilian astronauts travel to space, it's important that our environments are more than tightly pocket mechanical interiors of the International Space Station, which today represent the state of the art for long-duration human life in space. We also want to incorporate practical architectural elements such as access to natural light through windows and greenery. These were features that were missing aboard the space station when it was first commissioned, but which we know are critical to positive psychological functioning and well-being. For long-duration missions in deep space, it's important that crew members feel like they are living in a machine and more like they are living in a home. There are other ways of approaching habitat construction on Mars. Hard shell of inflatable structure may not provide the radiation protection that we need, and living underground in lava tubes doesn't quite support direct surface exploration on the planet. And also, why would you travel for 8 months to live underground? Designing structure in space is all about mitigating risks, and habitats that we create will need to be most durable and the most resilient structure ever conceived. Future off-world surface habitats will be self-regulating and self-maintained structures to support the crew members while they are there, but also to operate autonomously when they are not.